So in this video, we're going to start talking about weak topologies. So what are weak topologies? They are extra topologies one can put on a Banach space that are different from the topology given by the norm and have the key advantage of having more compact sets. So there are more sequences that are going to converge for this topology. We will say that they converge weakly than sequences that converge for the norm, for which we will say that they converge strongly. And in particular, we're going to build up to a very fundamental theorem called the Banach-Alaoglu theorem that tells us that for a sufficiently weak topology called the weak star topology that's only defined on dual Banach spaces that are dual of another Banach space, the closed unit ball is always compact. So from boundedness, we will be able to extract weak star converging subsequences, which is something extremely helpful in practice. Now, the reason why we're doing this is because the topology of the norm definitely doesn't have these good properties. In fact, in the first theorem, we're going to show that if the unit ball were to be compact for the norm, then the dimension of the space will have to be finite. Now, it's actually an if and only if. Of course, in finite dimension, closed bounded sets are always compact. So what we are saying here is that this characterizes finite dimension, and we have no hope to get this compactness from boundedness and closedness as soon as we are in infinite dimension. So this is the first thing we need to prove, because if the unit ball were to be compact for the norm in some Banach spaces, then we really wouldn't need all these weak topologies. And we need them precisely because this fails. So in order to prove this first little theorem, just to motivate what comes next, we are first going to prove this lemma, which is kind of a baby version of the Riesz lemma, right? It tells us that when you have a closed subspace, a proper closed subspace of a Banach space, then you can find vectors on the unit sphere of the Banach space that are far from capital Y. Now, the only difference with the Riesz lemma we've seen in Hilbert spaces is this epsilon. So we're not going to find vectors on the unit sphere that are at a distance exactly 1 of the subspace, but only at distance 1 minus epsilon. So let's say you can always find vectors of norm 1 at a distance 1/2 of the subspace. So that wouldn't be good enough in all applications, but that's certainly going to be good enough for many purposes, including proving the theorem 8.1. So let's start with the proof of lemma 8.2. So to do that, I give myself an epsilon, and I give myself a vector, let's call it x0, which is in the complement of y, right? And now I'm going to denote the distance between this particular choice of x0 not in y and y. And let me remind you, of course, that this is the infimum of the x0 minus y for all y running in y. So what I can do is I can pick a y0 in a y that almost realizes that distance. So I can pick it such that the distance between x0 and y0 is almost the infimum. So let's say it's equal to d divided by 1 minus epsilon. 1 divided by 1 minus epsilon being some number slightly greater than 1, depending on my epsilon. Okay, so now I'm going to define, or certainly say smaller than this. Now I'm going to define x to be the x0 minus y0 divided by its norm. Right, now x0 is not in y, so this is certainly non-zero, so I'm not dividing by 0, and in this way I'm certainly creating a vector x of norm 1. Now, if you give me a y in capital Y, what can I say about the distance between x and y? Well, it is 1 divided by x0 minus y0 times x0 minus y0 minus x0 minus y0 times y. But now the point is that this here is certainly an element of y, because y is a subspace. So x0 minus this particular element is something that's going to have to be greater than the distance from x naught to y. So this is 1 upon x naught minus y naught times the distance between x naught and y, which I've denoted by d. And now 1 upon x naught y naught is smaller than d over d minus epsilon. So this entire thing is greater than d divided by 1 minus epsilon, which is 1 minus epsilon. So that was a simple lemma. The fact that we give ourselves an epsilon of room compared to the actual Rees lemma makes things easy because we don't need to really project on the subspace. We just have to use the definition of the distance as an infimum, and the construction of the projection is, or the construction of the vector that realizes the 1 minus epsilon distance is fairly simple. Okay, now that we have that, we can prove our key theorem. We can prove theorem 8.1 and show that the unit ball of Banach space is only compact when the dimension is finite. So how do we do that? Well, we go by contradiction. We assume that the dimension of X is infinite, and then if it is, then we can produce a family of subspaces, a nested family of subspaces. So closed subspaces of X such that xn, so nested, such that xn is included in xn plus 1 and is not equal to xn plus 1 for all n. Right? If you are in infinite dimension, you can do that. The way you construct the next one is just by adding one dimension. So if that's the case, then this baby version of the Rees lemma is good enough to guarantee that for every n in n, there's going to exist an xn in capital Xn, which is of norm 1, okay, and is at a distance, maybe I should write it like that, an xn in xn plus 1, which is of norm 1, and which is at a distance at least 1/2 of the previous subspace. But now this gives a sequence such that for all n and m in n, xn minus xm is always at least 1/2, right? Because the xn and the xm, okay, when n is not equal to m, live in different subspaces, and the distance of xn to any of the previous subspaces is at least 1/2. So xn does not have a converging subsequence. Right. Therefore, the unit ball could not be compact if the dimension of the space were to be infinite. Okay, so the topology of the norm does not have that many compact sets, so we're going to look for weaker topologies that we can put on our Banach space that are going to have more compact sets. And the first one I want to define is the weak topology, and it's defined through a whole set of neighborhoods. So these will be basic open sets in my topology, and then I will look at the topology generated by those open sets. That is to say, the smallest topology that contains all of these sets as open set. Right. Now, these sets are defined in which way? Well, okay, they're your analogs of open balls for that topology, the neighborhood. So you give yourself a epsilon, which is the size of the neighborhood. You give yourself a point, which is like the center of the ball. And then you give yourself finitely many functionals in the dual. And you say that you belong to this neighborhood v epsilon x x1 star to xn star if the distance between y and x, not the distance in the norm, but y minus x tested against those functional is small, right? Is smaller than epsilon. So really the idea is that you're testing that y is close to x, but you're only testing in finitely many directions, right? This, if I were in finite dimension, I would not need arbitrarily many x star to test the norm of y minus x, right? I could just take the the canonical basis, and I would only have finitely many of them to test, and then by testing against all elements of the basis in finite dimension, I would know that y minus x in norm is small. But in infinite dimension, that is not the case, and I'm only going to define my weakly open neighborhoods by testing against finitely many elements in X star. But I can do that with arbitrarily many of those vectors. Right? So this is the typical open set for the weak topology. And then the topology generated by this set I denote by TW, and convergence in that new topological space, which is X endowed with that topology, I'm going to denote it by Xn converging weakly to X. Now we're mostly going to use this notion of weak convergence of sequences rather than advanced topological considerations. Nevertheless, we want to prove eventually in proposition 8.5 that the topology is Hausdorff in order to ensure that limits are unique when taken with respect to that topology. The first thing we're going to prove before that is that really what it means for a sequence to converge weakly, and that's probably simpler to understand maybe than thinking about the topology generated by this open set, this sequential characterization its description of the sequential convergence is just like that. A sequence converges weakly if it converges when tested against any element of the dual, right? So think of what happens in L2, for instance. You would be integrating your your xn minus x against another element of L2, x star, a fixed element x star. Okay, so let's start with the proof of this lemma 8.4. Right, so let's start with a sequence xn that converges weakly to x. Right, now, and I'm going to give myself an x star and capital X star, and I want to show that the sequence of real numbers xn tested against x star goes to x tested against x star. Now, what does that mean that xn converges weakly to x? Well, it means that for every epsilon, there exists an n, such that for all n greater than n, xn belongs to v epsilon x star. Well, it's a consequence of xn converging weakly. And that means for any neighborhood of x, such as v epsilon x star, if I go far enough in my sequence, I end up in that neighborhood. But what does that mean? Well, it literally means for every epsilon, there exists a capital N, such that for every n in n, xn minus x tested on x star is smaller than epsilon. And this is really just a reformulation of the fact that xn minus x comma x star goes to 0 as n goes to infinity. So that proves one direction of the lemma. Now, in the other direction, if I assume that xn minus x star tend to 0 as n goes to infinity for every x star in capital X star, and now I give myself some neighborhood, so I give myself an epsilon, some neighborhood of x, and I give myself a n in n. Maybe I should not call it n, let's call it capital N, and I give myself x1 star till x capital N star in x star. Now, what can I say about testing against any one of these? For every j between 1 and n, what have I got? I've got that xn minus x tested on xj star tends to 0 as n goes to infinity. So I could just say that given my epsilon, there exists a capital M in n such that for all n greater than this capital M, xn minus xj is smaller than epsilon, and I can do that for all j. So I can take a max j equal 1 to capital N, because this is a finite number, and that's very important that this number is finite here. And then what is that telling me? Well, it's exactly telling me that there exists a capital M such that for all n greater than m, xn belongs to v epsilon x, x1 star into xn star. And that choice of neighborhood was arbitrary, so right, I had fixed that at the beginning. So for any arbitrary choice of neighborhood that generates my topology, xn end up in that neighborhood for n large enough whenever this holds. So this concludes the proof of that lemma that tells us that weak convergence really is the same as the convergence of all these sequences of real numbers when you test against an arbitrary functional in your dual space capital X star. Okay, so let us keep going with these basic properties of the weak topology. So the next one is that the topology is Hausdorff. So how do we prove that? We give ourselves two elements, x and y, in our Banach space, x not being equal to y, and then I need to find an open set that contains x and an open set that contain y, such that the two open sets don't intersect. Now, what I can do is I can use the Banach separation theorem to separate x and y. And so I'm going to find an element alpha in R such that there exists an x star and capital X star such that x star tested on x is always smaller than alpha for all x. So for x itself, I'm separating the single point x from the single point y, and x star y is greater than alpha. Now I'm going to define V to be the set of all those z in x such that x star z is smaller than alpha. So x belongs to V and y does not, belongs to V, and now I want to show that V is a open set. So for any z in V, what have I got? I've got that x star z is smaller than alpha, so there exists an epsilon such that x star z is alpha minus epsilon, right? Now, if I look at the neighborhood v epsilon over 2 z x star, then what have I got? So if I take a z star, z tilde in v epsilon over 2 z x star, what can I say about x star z tilde? Well, it has to be smaller than x star z plus epsilon over 2 because I'm in this neighborhood here, and x star z is alpha minus epsilon, so this entire thing has to be smaller than alpha minus epsilon over 2, which is certainly smaller than alpha. So what I've proven here is that this neighborhood of z, right, is strictly included in V. So what we've got is that V is open. For any z, I can find a small enough neighborhood here of z, a neighborhood in the sense of the weak topology that's included in V. So V is open for the weak topology. It's weakly open, as we should call it. Right, now on the other hand, if you look at y, you have that x star y is equal to alpha plus some delta. Okay, and so if you look at v delta over 2 y x star, it cannot intersect V because it's still going to be something that's at least alpha plus delta over 2, so it cannot be smaller than, sorry, it's not different, equal the empty set. Right, so what have I got? I've got a open set here that contain x, an open set here that contain y, and these two open sets do not intersect. And that finishes the proof that the weak topology is Hausdorff. Okay, next on our wish list of basic properties from the weak topology, we have the following proposition. So we want to show that weak convergence implies boundedness. Now, obviously, strong convergence implies boundedness, but it's not clear a priori from the definition of the weak topology that this will include at least boundedness with respect to the norm. So let's prove that. Now, in the same way as we've seen the importance of the Banach, the geometric form of Banach, in proving the fact that the weak topology is Hausdorff, here we're going to use the uniform boundedness principle, and we're going to use Banach theorem again in that little proof of boundedness of weakly converging sequence. So you can see how all these cornerstone theorems of functional analysis are critical in setting up a decent theory of weak topologies. So how does that work here? Well, I'm going to define a sequence of linear maps from x star into R that take a functional x star to the duality product of x star with xn, given my sequence xn that is weakly converging. Now, for every x star in capital X star, what can I say about the sup of Tn of x star, say in absolute value, over n? Well, it is the supremum of the x star xn by definition, but I know that weak convergence implies that these sequences of real numbers here converge. So if they converge, then they have to be bounded. So this has to be finite because xn converges weakly to x, thanks to the proposition we saw earlier that this can be this is equivalent to all these sequences of real numbers converging. So this supremum has to be finite for every x in capital X star, and so the uniform boundedness principle tells me that the supremum of the norm of Tn as element of the bidual, really, so bounded linear map from X star into R, has to be finite. But what is that norm? Well, that norm is by definition the supremum of X star xn running over all X star in the unit sphere of capital X star. Okay, so can I get the norm of xn? How does that compare to the norm of xn? Well, we know by Banach theorem that for every n, there exists a norming function, right? There exists an element xn star in X star, in fact in the unit sphere of X star, that is such that X star comma xn is exactly equal to the norm of xn. Right, so that means that the norm of Tn, so the norm, if you want, of xn seen as an element of the bidual, is certainly greater than the norm of xn seen as an element of x. That's one way to see that x continuously embed into its bidual. So we have that, but we've shown that the supremum of the Tn was finite, and therefore the supremum of the norm of xn is finite too. Concludes the proof of this proposition. So weakly converging subsequents, of course, don't have to be strongly converging. Well, I say, of course, this is not completely obvious at this stage, but there certainly are weakly converging subsequents that are not strongly converging. But on the other hand, they at least have to be bounded. Okay, we're going to finish this video with a genuine theorem, which is due to Mazur, former student of Banach in the 1930s. And this theorem is simple to prove, but it's going to prove to be extremely helpful throughout the rest of the course. And it really connects these notions of weak topology with, the geometric idea of convexity. And what it it's telling us is that it's telling us that if we have convex sets, then the weak closure and the strong closures have to be the same. So let's prove this this beautiful little theorem. So let's start with one direction. So let's assume that E is weakly closed, that is to say that its complement is weakly open, and then I have to show that the complement is actually open in the sense of the topology of the norm. Now, what does it mean to be weakly open? It means that whenever I take an element X in the complement of E, I can find a small neighborhood of it that is included in the complement of A. So, okay, so there exists a delta, there exists an n, there exists n functional x1 star till x10 star in the dual, and they are such that whenever you have an element which is in this little neighborhood, so such that xj star tested against x minus y is smaller than delta for all j equal to 1 to n, then such a y has to be in E complement, right? Okay, now what does that give me? That gives me that whenever I have an x in E complement, if I pick delta to be delta prime, say to be the minimum of the delta divided by the norm of the x star j's, j equal to 1 to n. Of course, none of them have to be 0, if not you could remove it from the definition of the neighborhood. Then for every y in x, if x minus y is smaller than delta prime, then what does that mean? Well, that means in particular that x minus y xj star is going to be smaller than delta prime times the norm of x star j, which is smaller than delta. Okay, and that's for every j. And therefore, it's going to imply that y is in E complement. So what have we proven? We've proven that for every x in E star, the ball, in the sense of the norm topology, centered at x and of radius delta prime is included in E complement. Right, so we've exactly proven that E complement is open for the norm topology. Cool, so that proves one direction. Now what about the other direction? What if I start with a E complement that is open, okay, and I take an x in E complement. Right, now there is an entire ball around that x that is in E complement. E complement is open and E is closed. So by Banach theorem, I could strictly separate that x from E. So I could get that there exists an alpha in R, so, and there exists a x star. I'm separating by hyperplanes such that x star x is smaller than alpha, and alpha is smaller than x star y for all y in E. Okay, but then that means that my x here in E complement belongs to what is it, to V, which is the set of all those y in X such that x star y is smaller than alpha, obviously, and that V is weakly open. Right, we've seen that before. Now you fit a weak star neighborhood around any point of such a set. So V, oh okay, and V is weakly open, sure, and it's also included in E complement because all the elements in V tested against x star are below alpha, and all the elements in E tested against x star are above alpha. Right, and that concludes the proof of Mazur's theorem. So convex sets, for convex set, weak closure, weak closedness, and strong closeness are exactly the same. And as a corollary of that, we get the next corollary in the notes, which is that, it's immediate, which is that if I have a sequence that converges weakly, then I can always pick yn in the convex hull, a whole sequence in the convex hull of the xj's, and have this yn converge strongly to x. Right? So you can move from weak convergence to strong convergence by replacing your sequence xn by a sequence yn of convex combinations of the xj's. And the proof of that is immediate. It's just you take E to be the convex hull of the xj's, anything that can be written as a convex combination of xj's, and then you take its weak closure. And of course, X is in its weak closure, but the weak closure is the strong closure because E is convex. I took it to be convex by making it a convex hull. And so, X can be reached by a sequence in the closure in E. So a sequence of convex combination of the xj's. Right, that corollary is going to be something we use repeatedly in order to improve a weak convergence to a strong convergence, the price being that it's not for the original sequence, but it's for a convex combination of elements of the original sequence.